Okay, hello everyone and welcome. As you're entering the webinar today, please feel free to put in the chat where you're tuning in from. We'd love to hear where you are at right now, or what watershed you're in, more specifically. So again, thank you folks for joining us today. As you're joining, please feel free to put a little bit of information about you, where you're tuning in from, or what watershed you're tuning in from right now, or what watershed you work in. Fantastic. DC, Iowa, New Hampshire, Minnesota, Pennsylvania, Virginia, Indiana, New York, Ohio, New Hampshire, Maryland. Thank you all so much for joining us today. So we're going to get started because we have a lot of really amazing things to cover today. And we have two really great speakers who you'll hear from here in a little bit. So today's webinar is Rivers and Roads, Impacts of Freshwater Salinization. So I'm going to go a little bit of background information and then I will kick it over to our wonderful speakers today. So my name is Abby Heilman, and I'm the Salt Watch Coordinator here at the Isaac Walton League of America. And what we're here to talk about today is salt, specifically road salt. Every year in the United States, we apply somewhere between 20 to 30 million tons of salt on our sidewalks and parking lots and roadways. And we do this to stay safe during the wintertime, which is really, really important. But there is a bit of a balance between how much salt we apply and the environmental protection that we should really be considering as we're applying this salt, because that salt does in fact go somewhere. And a little bit of salt really goes a long way. And that salt, it does go somewhere. And whenever salt enters the environment, we consider it to be sort of more of a permanent pollutant because there's no feasible way to remove it once it enters the environment. So it only takes 1 teaspoon of salt to permanently pollute 5 gallons of water. If you're going to the store to purchase your road salt for the winter, you're probably going to be purchasing that salt in a 50-pound bag. A 50-pound bag of salt, if you use all of that, that has the potential to pollute 10,000 gallons of water, which is about the size of your residential swimming pool. Although we do need salt in the wintertime to stay safe, we can be a bit smarter about our salting practices. And that's what we're here to talk to you about today, and some of the impacts and stakeholders around road salt application. Something that we've noticed, this is a graphic that I took from WSSC Water, which is our local water utility, where my office is in Gaithersburg, Maryland. Over the past 30 years in the Potomac River, they have seen over a 104% increase of chloride concentration in the Potomac River, and over a 180% increase of chloride concentrations in the Patuxent River. And where they're testing these are actually right above where they're intaking water for their water filtration facilities before they pump that out to the public. So this is something that they've been keeping an eye on. This is something that a lot of our community groups have been keeping an eye on. And something that is really kind of an unseen pollutant once it enters their waterways. And so it's really important to monitor for some reasons that we'll talk about here later in the webinar. But also, you don't know what's happening in your own backyard, in your own waterways, unless you are going out and doing some monitoring. There are a number of different impacts that road salt has once it enters the environment. I'll go over a couple of these pretty quickly because I know we want to hear a lot more about this from some of our speakers later. So there are different wildlife impacts. A lot of those organisms, especially in those freshwater waterways, they're not used to salty conditions. And so when salt enters those waterways, that can certainly be a really big problem. There's a number of infrastructure impacts as well. Chloride is really corrosive, and it can corrode things, not only things like our appliances, but also our roadways, bridges, concrete surfaces, cars, culverts, pipes, stormwater infrastructure, and so much more. Each ton of road salt costs about $74. To apply that salt, it costs somewhere between $270 to $300. But then there's also a lot of sort of after application damages that occur from that road salt, damages to our the things that I listed above, the roadways, bridges, concrete surfaces, even things like our turf grass plantings and rainwater gardens and things like that. So every ton of road salt applied, it's estimated, and this is with adjusted inflation for 2023, between $1,700 and $17,000 in damages per ton of road salt used. So even though salt is really cheap to use, sort of from the get-go, it's really cheap to apply and purchase, that does have a lot of implications and a lot of damages after it is applied. And this can be a big issue for drinking water as well. Most water treatment facilities don't have the funding or the infrastructure to remove that road salt from the water. It's not something that can simply be filtered out. And so people who are on low sodium diets might not realize that they're getting additional salt from their drinking water, which can be a really big problem. Also, as I mentioned earlier, chloride is really corrosive. Water itself is very corrosive. Chloride is incredibly corrosive as well. If you think back to 2014, which was the start of the Flint water crisis in Flint, Michigan, part of the reason why that crisis occurred was actually due to road salt pollution. There's a number of things that went wrong during that situation. They switched their water directly to the Flint River in April of 2014. They didn't apply the proper amount of anti-corrosives to the water before pumping that out to residents, and so that chloride was able to corrode the inside of all of those pipes that were made out of lead and copper. Another issue too that some people don't think about is if you're on well water, that's something that is not regulated by the government. That's something that it's really on your own to go out and test. And so that's something that you should be considering if you haven't tested your well water recently, that you should consider doing that soon, just to really know what is in your water, so then you can stay safe. There's a number of habitat impacts, especially plants that are near sidewalks and roadways. They can really dry out, desiccate, and die. Salty soil is also can be compacted and less likely to retain water as well. And it's been found that chloride can mobilize a lot of heavy metals within the environment. So there's certainly a lot more research that's being done in regards to that. But so many impacts that chloride has in the environment. And of course, for those of you who walk your dogs or cats outside, there can be a number of pet impacts too. When they get that salt on their paws, it might hurt for them to walk on, but also if they lick their paws afterwards, that can cause some health concerns as well. There are a number of misconceptions about road salt, that more salt equals more melting, that you should feel that crunch of salt underfoot. But when you're looking at this picture here, these two pictures on the screen, the photo on the left, where there's just so much salt all over the place, that is way too much salt. You really don't need to apply that much. That much is going to damage your surfaces of your roadways and sidewalks, and it's going to cost you a lot of money in the long term. Whereas the photo there on the right, where it's just a sort of a sprinkling of salt, that's really all the salt that you'll need. And I'll break down sort of how much salt that is here at the very end of my presentation today. But a little bit of salt goes a long way. Something that we're trying to do about this is learn more about that road salt in the environment. So we send out free test kits to anyone interested in testing local waterways or even your tap water. You can use these for tap water. For chloride specifically is what we're looking for. Each of these test kits contains 4 test strips, instructions for how to take a sample, and instructions for uploading that data to our online database, the Clean Water Hub. And we do have a number of goals with this program to raise awareness in the general public about the connection between salt and stream health. A lot of people don't even know that salt is a pollutant, or really how it might pollute some of our waterways or even our drinking water. We're here to identify chloride hotspots in freshwater, identify some of these areas that are repeatedly coming back as really high levels of chloride, so we can take more action and do more testing in a lot of those areas, or find out really what the source of those hotspots is. And then, of course, to advocate for smarter road salt application as well by sharing some of our data results with private landowners and local and state agencies. Since our program began in 2018, we have collected almost 23,000 data points, which is really amazing. If you look at the map there on the left, the larger the data point, or larger the dot rather, there's more data points from those regions. And then the color of those dots corresponds with sort of our scale of chloride there on the right. And something that you might notice with this map is especially the more northern, very urban metropolitan regions, they tend to have higher chloride concentrations. And a lot of that is because they have more impervious surfaces on those sidewalks and roadways, and more surfaces that salt is applied to during the winter time as well. And then since July 1st of this year, we've collected about 1,200 data points. So a lot of data coming especially from Iowa, Ohio, and the DC metro region, but sort of all across the United States. And the breakdown, since I didn't go over this for the other slide, the breakdown of these data points, anything below 30 parts per million is below the scale that we can measure with our test kits, so we consider that to be excellent. Since we are a national program, we're considering anything between 30 and 100 parts per million to be fair. We realize that in some places, the sort of concerning amount of chloride in waterways is going to differ from place to place, but it said that anything over 100 parts per million is definitely considered to be anthropogenically caused unless you're in a region like Salt Lake City, Utah. So anything between that 100 and 230 parts per million we consider to be poor, and then anything above that 230 parts per million is going to start to be toxic to our freshwater aquatic life, whether chronically at sort of lower levels like 230 or acutely toxic or instantly toxic once it reaches up to something like 860 parts per million. But we'll have John especially talk a little bit more about that later in the presentation. And we're really hoping for all of this data that we're collecting to be turned into some sort of action, whether it's reducing salt on your own property if you are a landowner, or talking to your neighbors, your HOAs or condo associations to really inform them about how to save money and protect the environment while not reducing any safety aspect of applying salt during the winter time. And we do have quite a few resources that I'll share here in a moment, but also something to keep in mind is you can sign up for action alerts that we have. And Heather, if you can find a link for signing up for action alerts, I think that might be something we have readily accessible, hopefully. But the action alerts that we have, essentially when we see a bill at the state level across the United States, that are for reducing road salt pollution in the state, we typically create an action alert, which is a pre-written letter to one of your state representatives or state legislators to sort of tell them, yes, we want more bills at the state level to reduce road salt pollution across the state. So something to think about for this upcoming legislative session for your state. We also do have a number of resources from fact sheets, flyers, an advocacy guide, resources in both English and Spanish, template letters to representatives and to the editor, letters to the editor. And then toolkits for different groups like faith-based communities. If you're part of an Isaac Walton League chapter, you can also use that chapter kit if you're part of a watershed organization as well. And then, of course, things like event toolkits, like our Paint the Plow event that we had last fall, which was really fun and really successful. Some things that you can do at home to reduce road salt pollution is to shovel early and often to clear walkways before snow turns to ice. Scatter salt, a 12-ounce mug or your typical coffee mug holds enough salt to treat a 20-foot long driveway or 10 sidewalk squares, which is about 2 parking spaces. And then you can also sweep up any excess salt, store it in a closed container, and then use that during the next storm event, which reduces the amount of salt going out into the environment and saves you money as well. And Heather did put that link to learn more about the Isaac Walton League action alerts that you can sign up for if that's something you're interested in. And something that I wanted to mention too is in 2025, which is very quickly approaching, January 27th through the 31st is Winter Salt Awareness Week. So you can type in that link that we have listed there, or follow the QR code to learn more about Winter Salt Awareness Week. There will be sort of state and national speakers throughout the week. And then January 31st is actually a monitoring day where we're hoping that people go out, maybe contact your local or state press and media to get some media coverage about you going out and monitoring a local waterway during this week. So more information about that at wintersaltweek.org. So feel free to check that out because this is really, really an exciting event that we'll be having this year. And if you have any questions, feel free to visit our website, saltwatch.org, or email us at saltwatch@iwla.org. If you have any questions, please feel free to put those in the chat. And I'm going to go ahead and pass it over to our next speaker, who is Dr. John Jackson. So John, as you're getting your slides ready there, I'll give you a little intro here. So John Jackson is a stream ecologist and aquatic entomologist with 42 years of experience studying stream and river habitats that range from hot deserts and cold alpine mountains to wet tropical forests and hardened urban corridors. At the Stroud Water Research Center, he leads pioneering research into the effects of human activities on pollution-sensitive freshwater species like mayflies. His research on stream salinization dates back almost 20 years and includes studies of road salt, mountaintop mining, and produced water from hydrofracking. Sorry about that, from hydrofracking. So without further ado, John, feel free to take it away. And thank you so much for being here today.
Oh, it's pleasure is mine. If you don't mind, I'm going to stay off screen just because my computer is really heating up right now. Thank you all. We have a lot of people online. I'm really pleased to see that. Today, what I'm going to talk to you about are concentrations. I'm going to talk to you about toxicity. I'm going to talk to you about some implications, not everything, just those related to aquatic life. And much of what I'm talking about is I can't take credit for. I'm really drawing from so many pieces of work from colleagues and coworkers, as well as friends of the Stroud Center and just volunteers and partners throughout the region. First, I wanted to some of you, especially if you're new to this, might get confused. There are so many different terms bouncing around in this world of road salt and fresh water: salinity, total dissolved solids, conductivity, specific conductance, actual salt, whether it's sodium chloride, potassium chloride, calcium chloride, and then chloride, as Abby was just mentioning. And they're all related. They're not all the same, but they're all related. And so it can be confusing, but just keep that in mind, that they're all related. The other thing that people need to recognize is when we're talking about salts, one of the great things about working with fresh water or working with water is it is the universal solvent. And in the case of an ionic compound like sodium chloride, it takes these two ions and separates them. So the sodium chloride goes to sodium and chloride. Well, the most common salts in fresh water in most areas are going to be limestone derivatives or soluble rocks. So calcium carbonates or magnesium carbonates, and they separate to calcium and magnesium and then the carbonate. But with road salt, whether it's sodium chloride, calcium chloride, or magnesium chloride, these are the three primary salts. They're going to separate to a sodium, a calcium, and magnesium, and then you see this chloride. And this is why we measure the chloride. It's very easy to measure, and it's consistent. And most rock salt, most road salt, most of our de-icing salts are going to be sodium chloride. But you just need to be aware that the pet soft stuff or the hot shot stuff, are going to have either calcium or magnesium or both. As Abby said, I got started working on this question or this issue early in my career. And it was when we were working with just landscape gradients, urbanization. And somewhere along the line, we noticed this relationship between stream degradation in urban areas and elevated conductivity. Then we went and looked at mountaintop mining. Mountaintop mining is actually a different salt than road salt. It's a carbonate primarily, but the same thing happens. The aquatic insects in the stream struggle. And then hydrofracking came along. And one of the things that are produced by these well pads is this produced water. And it's very salty, very, very salty, very high in sodium chloride and some calcium carbonate also. With that exposure, that's all freshwater salinization. And we could also talk about other sources, agricultural or wastewater. The thing that jumped out at me in that first study on urban things, this is the Schuylkill River Basin, 150 sites. It's a great watershed to work in. It goes from being very forested and really good streams to impaired waters, either due to acid mine drainage or urbanization or really intensive ag. And on this gradient, we see this is just a plot of the macroinvertebrate score where at a high number, you have lots of species. It's a good stream. And a low number, you've lost a lot of species and it's a poor stream. And basically, as conductivity goes up, the number of species goes down, the stream becomes more degraded. The other thing in that data set, because we were working with some sites annually, by 2005 or so, we had several measurements of conductivity or salt, and it was going up. And at that point in 2005, nobody was really talking about this yet. And but somewhere between 2000 and 2005, I started seeing this. And so I was doing both conductivity as well as alkalinity and chloride measurements. The first paper that I became aware of road salt is 2023. And this was, as Abby was mentioning, drinking water in the Washington area or Maryland. This was drinking water for Philadelphia. And it was from 1973 to 1999. So many decades ago, they started collecting water intake data and they observed some really good things about the Clean Water Act. Phosphorus was going down, ammonia was going down. But maybe unexpectedly, they noticed that sodium and chloride both doubled in this 27-year period. So for more than 20 years, we've known that this is a problem. But in doing a little research, I actually discovered that we shouldn't have been surprised at all. The visuals were there, but as far back as when the Clean Water Act was first passed, people were paying attention to street salting. So this is 1970, a National Academy of Science report looking at the impacts of de-icing salts on water quality and the biota. 1970, 2 years before the Clean Water Act. So here's a bunch of 70s. Here's a paper early 1990s on groundwater contamination, early 2000, groundwater contamination. People were paying attention to this long before I was. And that's because, this is like the pollutant that's hiding in plain sight. You're applying tons and tons and dump truck upon dump truck of this onto the landscape. It all goes away, but it really doesn't go away. This is a graph of the tons, it's million metric tons per year, starting in 1940, and we've updated this all the way to 2022. The thing that's so striking is that this wasn't a problem early on, but by 1972, we were applying about 5 times more salt than we did pre-1960. So there was a rapid increase between 1960 and 1972. It was stable for a while. Now we're at 12 times what we did in 1960. So if you were to talk to your parents or grandparents or great-grandparents, they would have said when they were a kid, road salt wasn't even used. Well, like I said, it doesn't go away. It actually goes into our streams and rivers and our wetlands. These are data. This is what's been applied in the US. These are 3 streams outside of Philadelphia that we have really good old data going back to the 40s or the 60s before salt became an issue. And what jumps out at you is the increases. So now in this rural stream, this is where the Stroudwater Research Center is, White Clay Creek. It's all agricultural, only 2 or 3 roads, and we're not accumulating salt in these streams. Whereas the blue lines are about tenfold what was observed before road salt became commonly used, and an urbanizing stream 30-fold in Valley Creek. And this difference is really about the dominance of roads and parking lots in the watershed. So the greatest increase in the area that has the most roads and the most parking lots, and therefore the most salt accumulating. But it parallels, no matter how you look at it, it parallels our use of road salt. Another way of looking at it, this is data collected by our volunteers. This is just chloride versus impervious cover from one week of sampling 108 sites. You increase roads, you increase parking lots, you increase contamination. But notice these numbers that I'm showing you, and we'll get back to this in a moment. We're talking about 150 milligrams per liter chloride when we started at 5. And this is where the volunteers have come in to help us. We work with 50 groups. We probably have 150 volunteers total. We have them doing grab samples. We've had them monitor sensors for us, continuous sensors that measure conductivity, temperature, and water depth. It's really an army of helpers. It's with these helpers we saw one of our first really big spikes. This was in First State National Historic Park in Delaware, and the volunteers picked up a peak that was over 40,000 microsiemens per centimeter. That is almost seawater. This is a 4-day average at 20,000. Again, conductivity background might have been 150 as opposed to 40,000. Then another group, this is just north of Philadelphia, the TTF Watershed Partnership put in a sensor near a parking lot. They had 3 spikes. This was 2 years ago. The second spike is nearly twice seawater. And if you translate that to chloride, which is one of the measures that you guys can learn to use with Isaac Walton League, instead of 5, maybe 10, you're at 18 to 42,000 milligrams per liter chloride. This spike is through the roof. Now, you need a continuous sensor to grab these things. You can never see it. You just have to be sampling constantly. But we have used the volunteers to look at groundwater contamination. And these are 3 different groups. Back a year and a half to 2 years ago, looked at anywhere from 30 to 108 sites in a day or two. When it's late October, November, January, no storms had occurred, no new road salt. These are the data that we measured in this landscape. Whether it's 30 sites or 100 sites, we see a lot of salt, commonly over up to 200 to 300, and even our lowest areas are still showing a lot more salt than would be normal. I drew in 2 lines here. The 230 is the EPA standard from 1988, and the 50 milligrams per liter chloride is a standard that Maryland and Ohio have used in some circumstances. And one way of looking at that is that's 10 times as much salt as might have been in there under normal conditions or pre-development conditions. If we use the EPA standard, we have a handful of sites that are too salty. But more interesting, if we use the Maryland and Ohio standard, almost all the sites are dealing with salt stress. That salt is adding to the stress of these urban suburban streams. So that leads us to the question, how much? How much is too much? A lot of what we know has been based on standard lab animals. And what we've done at the Stroud Center is work with some of our native mayflies, brought them into the lab where we can hatch eggs, get first instars, and in a matter of 30 days or so, drive them all the way to complete their life cycle to the adult stage. So it's really convenient test animals that we have in the lab. And what we've done is we've done dose response curves. This is the same thing we do with human testing, where we put in a stressor, in this case chloride, and we look at survivorship. And if there's no chloride, we get 100% survivorship. And if there's a whole lot of chloride, everybody dies. And this is just a test with aquatic life. And then what you do is you pick the spot where half of your individuals die. And at that 50%, that's a lethal concentration that results in 50% mortality. That's the start of a regulatory standard. That's not a protective standard. That's just a standard that we can talk about. Protection is going to be obviously something less than that, and they tend to poke around here in the no observed or little observed effect. Well, we looked at the age of animals, the duration of the exposure, the stream types, hard and soft water, different mayfly species, and temperature. We found that all of these are important to toxicity, but 3 of them were more important than others. The duration of the exposure, a few days to a month. The stream type, if you increase the duration, you increase the toxicity. If you increase the hardness of the water, you decrease the toxicity of salts. And finally, if you increase temperature, you increase the toxicity of salt. That last number is a nice piece of information, because that means the higher winter concentrations maybe are less lethal than they would appear to be based on lab bioassays that are done at room temperature. The one thing we did was only work with sodium chloride, but the other salts matter, that they're not all equal. So these are some older data actually for 3 test animals, and I've just highlighted here, this is the LC50, so lethal concentration, which would kill half the animals. And magnesium chloride for this, these are 2 zooplanktons, and this is a fish. They're way more sensitive to magnesium chloride than they are to sodium chloride, as an example. So the type of salt can matter, and we just didn't look at that, but it's something to keep your eye on. How to answer this question? Well, the Canadians revisited this, so the EPA did it in '88. The Canadians revisited it in 2011. For short-term exposure, they came up with 640 as their standard, and their long-term standard was 120. Now remember, that 120, that's less than 230 from EPA, but that's greater than what's come out for Ohio or Maryland more recently. And one of the things that's affecting the more recent surveys is maybe that we have more data. This was all available data that the scientists trust. We added our mayfly data here, and our mayfly data for short-term exposures landed on top of what everybody else had found. But for a longer-term exposure, in our case, 30 days, what we found was our mayflies ended up being quite sensitive. And mayflies are universally accepted as being kind of indicator organisms. So most of the animals that are scoring here on the more sensitive end, so they're responding to less chloride than some of these other taxa. Mayflies and mussels, juvenile mussels, they can now work with those in the lab, and those data have also influenced what we know about aquatic insects or aquatic macroinvertebrates being sensitive to salts. That would be true over here too, that your freshwater mussels are over here on the sensitive end. So top of the curve, really tolerant, bottom of the curve, very sensitive. So this question is still to be answered. It's not clear, although it is pretty clear that the 1988 standard, given the new data that are available, it's probably not protective for many of our sensitive species, but it's the standard that we have. And until it gets replaced, that's what we're working with. If a state replaces it, you can work with your state standard, but in many cases, the states are still relying on the '88 EPA standard. And I mentioned this before, this curve, macroinvertebrate score versus conductivity. As we increase the conductivity, we decrease the quality of the stream. We lose taxa. So more salt, fewer species, lower score. But it's important, even as amateur scientists, to remember that correlation may not equal causation. And it's so easy for us now to measure chloride or to measure salt with a conductivity meter. But it's important to remember that water just, or salt just illustrates this connection that we have. But it's not the only toxin. We have oils, metals, sealants, herbicides, insecticides, personal care products. We have them coming in through the storm drains. We have them coming in through the sewer system. Even your sewer system is delivering a bunch of salt because we live salty lives. So it's important to remember that salt's not the only thing out there. It's just one we can measure easily, far easier than measuring pesticides, for example. So the things to remember from my presentation, first of all, sodium chloride is increasing in the streams and in our groundwater, especially in urban areas. At this point, current levels can be causing physiological stress or even be toxic. The brief spikes in the winter that we see, though, are not well understood. We haven't done that science enough yet to really know what that means. The impact depends on stream hardness, exposure duration, and water temperature. So if you're seeing these new data coming out of wetlands, for example, think about the exposure. If that wetland is salty for day after day after day, that's why they're seeing some toxicity there. Or at least that's how it's different than a stream, which would wash it through. And finally, we're not done defining salt limits. There's more to be done, but this is a pollutant that we can measure. And it's certainly a great tool, both in terms of highlighting that we're having an impact on the stream, and also there are things that we can do about it. I don't know if, Abby, you want to move on and answer questions at the end. Your call.
Yeah, if anyone has any questions, please feel free to put those in the chat. And I think we will go ahead and answer those questions. Actually, there's one question right now, if you have a minute to answer this, John. Why does
Sure.
alkalinity buffer against chloride toxicity?
You know, that's not well understood, the physiology of the competition, but it has something to do with the calcium and the calcium interacting with what's going on in this osmotic or balancing out. So when we add sodium chloride, it's what we would call a water balance challenge more often than not. It's not about being toxic. It's about screwing up the salt water balance inside the animal. And somehow adding calcium carbonate reduces that water imbalance.
Thank you. I think we'll hold additional questions until the very end, but please feel free to put any additional questions that you have there for John. And I'll go ahead and introduce Megan here in a moment. So again, if you have any questions, please feel free to put those in the chat, and we'll make sure that we have some time at the very end to answer those. So Dr. Megan Rippy is an assistant professor in civil and environmental engineering at Virginia Tech. She received her BS in marine biology from the University of California, Santa Cruz, and her MS and PhD in marine biology and oceanography, respectively, from the Scripps Institute of Oceanography. Her work focuses on characterizing and modeling green infrastructure services, including phytoremediation of salts and their socio-ecological drivers. She is committed to collaborating with stakeholders and communities to solve emerging environmental challenges like inland freshwater salinization that pose a growing threat to our infrastructure, people, and the environment. So without further ado, I'm going to turn it over to Megan. Thank you so much for being here today.
Happy to. Just to check, can everyone hear me?
Yes, you're good.
Awesome. All right. So let me make sure I hide my meeting controls so that I can see everything. I'm, as introduced, Megan Rippy. I'm an assistant professor at Virginia Tech, but instead of being down in Blacksburg, I'm actually up in Northern Virginia at the Occoquan Watershed Monitoring Lab. So I'll be talking a little bit about the Occoquan today, but really focusing on collaborative opportunities for managing salt and what we might be able to do about this freshwater salinization problem. As we've heard, many of the nation's freshwaters are salinizing. I just love this figure from the United States Geological Service that illustrates, particularly, along the East Coast, all of these little red triangles are increases in specific conductance in streams. The magnitude of the problem in this area. And where I am is actually in Northern Virginia, so at the Occoquan. And so this is a real problem for where I am. And to give, a very local example, so I mentioned that I'm at the Occoquan Reservoir. This bit that I'm circling here, I'm hoping you can see all the arrows that I'm moving around here. But that's the Occoquan. It's fed by two streams, Occoquan River and Bull Run. And there is an intentional indirect potable reuse, so a discharge of wastewater, highly treated wastewater, to Bull Run that makes up part of our system. And Fairfax Water, is a water service authority. They provide drinking water to about 1 million people or more in Fairfax County. So what's going on in this drinking water matters a lot from a water quality standpoint. And we've been seeing sodium levels. So I'm focusing a little bit, switching salts for you from chloride to sodium. We're seeing sodium levels in that drinking water increase over time, and those sodium levels are beginning to exceed both the EPA's health advisory for people on low sodium diets. That's the sort of dashed line here on the plot to the right, and also the taste threshold. Sort of that lowest taste threshold that we have. That's that solid black line. And looking at Fairfax Water's intake, that's what's in purple. So we've got sodium concentration on the y-axis and time on the x-axis here. You can see in the 80s and the 90s, the water was pretty good from a sodium perspective. It's below both of these thresholds. But moving in, to the 2000s, we start to see regular exceedances of that, health advisory for people on low sodium diets. And now we're also starting to see exceedances of that taste threshold. So people are beginning to taste the salt in the water. So it's a real problem for the water utility or water quality perspective. Okay. So what can we do about this? One stance is to come at it from a regulatory angle, setting thresholds. We've heard a bit about this today for chloride. Sodium ion concentrations are a bit different. They're not regulated at the state or federal level. And I would argue that this is unlikely to change in the near future because the US EPA actually evaluated sodium as a potential candidate for regulation in 1998. And it decided at the time that setting sodium thresholds didn't present a meaningful opportunity to mitigate health risks. And, salinization has worsened since this determination. We now recognize that concentrations of sodium that were previously considered low, like in the 30 to 60 milligram per liter, do have adverse health consequences, things like preeclampsia. But because we have this 1998 ruling that kind of makes federal action, less likely. There are a lot of other contaminants in line before sodium could be revisited, some of our PFAS compounds and things like that, that are also, very important. But because of this, context, it makes locally tailored kind of collective management by stakeholders, all of you, water utilities, county agencies, transportation authorities, general public, and the like, these bottom-up actions, really critical for managing inland freshwater salinization. And that's really what one of the big projects I've been working on has been focusing on. It's what's known as a growing convergence research project, where the whole goal, was to catalyze stakeholder-driven bottom-up management of freshwater salinization in the Occoquan system, where we're located. And it's a collaboration between, 50 or so stakeholders and then researchers at Virginia Tech's Occoquan Watershed Monitoring Lab, just trying to build a shared understanding of what we call the social ecological system. So all of the ecological components and all of the people components, of the freshwater salinization challenge, so that we can work towards solutions in the absence of federal regulation. And, there's multiple parts of this project. Some of it's really focusing on, sources of salt and fate and transport processes through monitoring, data analysis, and modeling. But there's also this element that's just on shared understanding, how we might build shared understanding and identify areas that are ripe for collective action now. And that's really the part I want to talk about today. So our approach for building shared understanding, we started by convening a stakeholder working group. All the individuals we could gather that had a vested interest in freshwater salinization in this system. And they came together and formed what's known as the Executive Committee on the Occoquan System, or ECOS. And we worked with these stakeholders to map out their mental models, kind of their perceptions of this social ecological system for the Occoquan. They identified the dominant causes, the consequences of salinization, the kinds of actions that they thought could be best taken to mitigate salinization, and then mapped out all the interrelationships between them, creating just a little model of how the system worked according to each person. Because the goal is you can take all of those different models and identify, the areas where people agree across them. And those are areas where collaboration and collective action seems likely. And then there are also areas of disagreement that could be barriers, collective action, or, alternatively, opportunities for shared learning, places we need to, talk about and focus on. And so the first part of this process was just assembling ECOS. Had really diverse representation across utilities, counties, state and federal agencies, non-governmental organizations, the like. All of the groups here were participants, at some point. About 35 to 50 members at any given time. There's some rotation, with membership that goes on too, because of time availability and the like. And then for actually, going through and interrogating people's perceptions, of the system and identifying, shared and divergent perspectives, you can think of this as kind of a cyclical co-production process. So we had, 35 members of ECOS who were willing to participate in this, and we all got together and worked on identifying, the dominant causes, consequences, and mitigating actions, that might matter for freshwater salinization. Not everybody agreed on all of these, but what are the biggies, that we can put together, into a big concept list. And then everybody kind of privately, worked on their own, mental model of freshwater salinization. We call these fuzzy cognitive maps, where they picked the causes, the consequences, and the mitigating actions that were most important to them. And then they mapped them all out, drew the interrelationship, so that you had a little model, of how the system might work. And then we looked across these models. And when we're thinking about, shared perspectives, you're looking for concepts or relationships that are repeated, kind of by everybody. And then in terms of divergent perspectives, we used some statistical tools to break out groups of stakeholders that had significantly different perceptions about the system, created what look like little yarn balls here. Those are just models, of people's different perceptions. You can see they get quite complicated in some cases. And the reason this is cyclical is you can show those models back to everybody. It daylights those like hidden, perceptions, things we might not otherwise articulate. People can work together to refine and reevaluate concepts, and the cycle continues along, as we learn. And the goal with all of this, again, was just to identify areas of agreement that might be these opportunities for collective action, and then areas of disagreement that could be barriers or even opportunities for shared learning. Okay. And I want to start by presenting kind of these, opportunities for collective action. And that's what this Sankey diagram is showing. It looks a little, cluttered and confusing, but really all you're looking at in these little gray boxes, these are all the concepts that were present in more than 50% of the stakeholder, mental models of salinization. So these are the things that people agreed on. And then the colored connections are the relationships that they'd agreed on. Anything that's in blue has to do with salts, added to the watershed. So these are our de-icing chemicals added to roads, things like that. These are the relationships illustrated in blue. Anything that came from the sanitary sewer, John mentioned real briefly there, the sewer shed, inputs, the products that we use in our homes that are salty, and the idea that wastewater treatment doesn't remove salts particularly well. There were a couple, connections here identified in yellow, for those, but, a little bit weaker. And then those pathways that could impact both, were highlighted there in green. All right. And just looking across all of this, what I want to draw your attention to is that one of the things people really do seem to agree on in this system is that winter salt management is important. 89% of people, the most common, action mentioned was the need for winter maintenance BMPs. And that includes a wide range, things in that category, but people agreed that focusing on this was really important. They also agreed that dominant causes were things like winter maintenance chemicals added in the public sector for de-icing of roads. This would be like VDOT or, one of your sort of agencies, at the state level who is adding salts, to highways, public roads. Also, 91% was more, winter salts added in the private commercial sector. So like parking lots for malls and things like that. And then the homeowner, 86% for your private salt application to your roads. These were, dominant, kind of across the board. Winter salt management is kind of an opportunity, for collective action. In terms of what we disagreed on, and there were divergent perspectives, there were four, groups actually that characterized different ones. I'm going to focus here just on two, for time reasons. And this mental model, I've kind of grayed out, things that were more shared, across different people's perspectives, and just highlighted those concepts, that were different. And this group really de-emphasized, the salts applied for winter maintenance purposes in the residential sector and in the commercial sector. So de-icing activities, they de-emphasized though, and they favored, focusing on indoor products. They thought that use of products that we pour down our drain that go into our sanitary sewers and go into our waterways may be a particularly important thing to focus on, in the aquapon system. They also de-emphasized regulation, as a management tool. They were more interested in, kind of bottom-up management approaches than putting together new regulatory standards. So that was kind of group A. Then we've got group B, and they were actually saying, no, it's winter maintenance chemicals. We really need to focus on the residential and the commercial sector, and regulation is going to be our primary tool, right? Regulation here. So they were really focused on that. So we have these two, very divergent opinions that you can kind of sum up as saying that we disagree on the relative importance of watershed versus sewershed salt sources. Do we need to be thinking about in-home products and water softeners and industrial discharges and things like that, or not? And we disagree about the appropriate mode of governance. Are we going to need to fight for formal regulations as the best option, or should we strive for collective action now? Disagreement about that. And we can leverage these areas, I really argue that we can, into opportunities for shared learning about freshwater salinization and the aquapon by targeting some of our future research towards these questions, towards sewershed salt sources, towards alternative governance arrangements, to try to understand, whether or not they matter. Maybe we can resolve, some of these disagreements by putting a little bit more effort into some of these areas. So at this point, what we've identified is, some areas of agreement, where research is still required, but these areas are likely to be actionable now. And that's really management of winter maintenance chemicals. Some of the stuff that's been talked about, extensively today is an area of agreement. And we have these areas of disagreement also, where more research and deliberation is needed for the topic to even be actionable. And that's sort of our sewershed and, governance approaches. And I wanted to take just a tiny bit of time to provide a concrete example of each. On the managing winter salt side, this kind of, areas of agreement, I want to talk a little bit about phytoremediation because it's kind of near and dear to me. And then on the areas of disagreement, kind of zooming in on the sewershed and thinking about the in-home products we use, and some of the salt content in those products. So looking at, kind of winter salt management, often we have a tendency to focus on what are known as supply side approaches. We're trying to keep salt out of streams because if we can do that, that is going to be cost effective and it's going to reduce, the amount that we have to remediate later. And a lot of these, if you haven't seen this document, it's really worth looking at. It's a salt management strategy for Northern Virginia, and it details, a lot of these different types of supply side approaches and talks a little bit about their effectiveness. Phytoremediation is kind of on the other side of this. It's a potential way of managing the salt that we do apply so that we can help remove some of it after it has got into our stormwater. Okay. And the interest and growing interest in phytoremediation comes out of this recognition that green infrastructure practices for managing urban stormwater have really taken off. They're increasingly common. So we'd like to know, can the plants, present in these systems help mitigate freshwater salinization? And this, work, I'd argue, is actionable now because it has, been written in sort of legislatively, Virginia General Assembly kind of Commonwealth's natural resource budget. So people are starting, to move on this, at higher levels than, I personally occupy. And the kind of work that was funded, things like plant surveys and phytoremediation assessments across 14 or so bioretention systems in Northern Virginia. And these are systems that drain different land uses. So we have really big highway sites, highway detention basins that drain large roads. We targeted some of those sites that drain parking lots to get that kind of input. And then as a control, there's sites that drain more pervious areas because we recognize that there are geologic sources of salt, and also there's going to be less, anthropogenic impact here. So looking at phytoremediation potential across all of these. And in terms of what we found, whether phytoremediation can actually help us manage freshwater salinization, I kind of want to break this into kind of the good and the bad news, because there's a little bit of both here. So the good news is that the plant community analysis did identify a bunch of native plant species that are salt tolerant and could potentially help mitigate salt in green infrastructure. There's native plant species that can do some work for us. I've listed some of the common names of different growth forms here, and we've got a couple pictures to the right to show you what some of these plants look like. That's good news. And some simple calculations that we did based on the concentrations of sodium and chloride observed in plant tissues illustrate that maybe a standard size highway bioretention basin, maybe we're talking 2,000 to 3,000 meters squared, that if we plant it with a halophyte-like cattail, it could phytoremediate up to 100 kilograms of sodium and 200 kilograms of chloride per year, and that's equivalent to the weight of about 1 to 2 adult people. Okay, so that's a fair amount of salt. Imagining you being carried out of the system, each winter. That is a meaningful amount. The problem, and this is the bad, right? The problem is that the amount of salt that we actually use that is entering detention basins in kind of a snowy winter year in this area is around 2,100 to 2,900 kilograms of sodium and 3,200 to 4,400 kilograms of chloride. So phytoremediation is only removing about 5 to 6% of what's applied. So you could say that it's unlikely to be kind of this one-stop shop for reversing winter salt pollution, but we wouldn't really intend to use it that way anyway. It's this viable kind of low-energy tool in our toolbox in combination with others can help mitigate the problem. And the other thing that's important to recognize is it may be one of the cheapest, 5 to 6%, removals that we can get, just, given that you're moving past plants to think about structural measures, and structural measures tend to get more expensive. Okay, so that's sort of our little vignette about, sort of the area that is actionable now, phytoremediation. I want to really briefly, talk about sort of the second kind of area of disagreement focus, looking at the sewer shed, and turning our attention to laundry detergents as an example in home product. And I should emphasize that all of this is really preliminary because, thus far, the salt content of only around, 20 detergents or so has been evaluated. And, we're just focusing on products that are most used by communities in Northern Virginia and DC, as determined through a survey of about 600 people or so. That includes things like Tide, Gain, Arm & Hammer, All, and Seventh Generation, alongside a bunch of more bargain products. And they're particularly interested in formulation, so looking at the differences between free-flowing liquids, some of our liquid packs, you might have heard them as pods, free-flowing powders, and then powder packs, which are just encapsulated powder in a format that is similar to pods. It just has a powder in it instead of a liquid. Sorry about that, guys. There we go. And what we're finding, looking at these different products, is that the formulation does really matter. Our powdered products tend to contain, 10 to 100-fold more sodium and chloride than the liquid or liquid pod kind of, formats. And that's because sodium sulfate and sodium chloride, that's a little bit rarer, but sodium sulfate often tend to be used as bulking agents. In the powders, you can just look at, the amount, of sodium in sort of these powders and powder packs. This is just kind of a maximum here. Versus the amount that we're seeing in liquid and liquid packs, and it's a big difference. Such that switching the products that we use in the home could potentially reduce salt loading to streams from treated wastewater, the salts that just pass straight through our wastewater treatment plant processes. Big question here, how willing are people to actually switch the products that they use? Most people report, just again from this little survey of 600 people that we did, that they're kind of somewhat likely to switch if presented with new information on the environmental impact of the products that they use. So there is some hope here, but there are, a fair number of people who are not likely to switch as well. And it's a real open question of how much it would matter if they did. This is a subject of ongoing research. People are trying to understand how big, the impact of the sewer shed is and the residential project products that are discharged so that we can understand, the role that the sanitary sewer plays in the freshwater salinization story. This is something that's really important to get a handle on. Okay. So just to summarize and conclude, we found that the majority of stakeholders in the Occoquan system feel that winter salt management is important. So salt application to roads and everything you guys are doing, it's a really actionable topic, right now. And this includes, managing some of the salt sources through things like training programs and, tracking what we apply, salt application rate management, stuff like that, and all those things that are articulated in SAMs. And then also approaches for remediating, what salts we actually do apply that get into our stormwater and into our environment. Phytoremediation is a potential partial solution, but plants aren't going to be able to solve the problem on their own. We probably need to lean heavily into some of these source management, approaches and just leave a little bit left, for the plants to do. We found that stakeholders disagree about the importance of sewer shed salt sources and how salt should be governed. And this is all, part of really exploratory kind of research phase work. The efforts that have been done to address in-home products and their relative contribution to salts in the sewer shed are things that are underway. It's promising work. Could help us understand whether, we need to do source switching programs and, stuff of that nature. So to switch our products. And additional research efforts in this area, though, are really needed if we want to understand the sewer shed's contribution to salt pollution, because we'd really like to transition this to an area of agreement that could potentially be actionable so that we're focusing both on, watershed applications, de-icing chemicals and the like, but also what we're using at home and what we can do there so that we're managing both sides of the equation. And with that, thanks to everybody, and I can take questions sort of when that's ready. I want to thank all of the people also who are involved in this project. I did not do all of this work on my own. There's a bunch of wonderful students and other faculty members, and then I could have put 50+ stakeholder pictures on here as well, but we're trying not to say who everybody is. So thank you if you're on this particular call right now. You know who you are.
Thank you so much, Megan. That was a great presentation. And I know we sometimes mention the different sources of chloride too. So thank you for going much more in depth about a lot of those sources as well. We are a little over time. We did start a couple minutes late today. So I totally understand if you need to go. And for our two speakers as well, I want to be respectful of your time. So if you need to head out, I can send you some of those questions for the chat too. If you're okay to hang on to answer some of the questions, that would be great. But sort of let me know where you are time-wise. And again, this presentation has been recorded. And so I'll send out the link of the recording here after this too, if you do need to leave early, and if your question hasn't been answered until sort of after you've left. So are you guys okay to hang on for a little bit or, okay. Megan, you good too? Okay, perfect. So if you have questions, please feel free to put those in the chat. I'll start sort of from the top of some of the questions that we didn't answer yet. And thank you for all of these great questions that are here in the chat. So I think this one is for John. Well, I guess either of you really, would riparian buffers be effective in mitigating the effects of salt in our streams? So
Well, if
let's take that.
I can steal a little bit of Megan's data, and if you just look at plant uptake in a stormwater setting, the buffer is not really going to be an answer. Certainly not at the levels that we're looking at, and especially in an urban setting, most of your water's not going through the buffer. In terms of road runoff, it's being piped right by it. So unfortunately, no. They're just not, they don't have a chance.
Megan, did you want to add on to that at all?
Just in terms of like riparian buffers.
Hmm.
Um,
Yeah.
um, I think there's different perspectives on this. I would tend to agree that what the plants are going to be able to do is at least in a above average kind of salt application snow year, going to be relatively minimal. And the situation does differ a little bit between like a riparian buffer and like a detention basin where you've got things pooled and held for a little bit longer. So it may actually be a worst case for the riparian buffers. But then again, there has been some work by Sujay Kashal and the like that suggests that riparian buffers can do a certain amount of phytoremediation, though it's not 100% sure what the plants are doing versus what you're getting salts bound into the soils there, and how rapidly or slowly they're released, over time, subsequently, how permanently we'll say removed that would be. And we have that same problem with permanent removal when we start talking about plants, because this only works if you harvest, the vegetation and you take it away. Otherwise, when they senesce, they can reintroduce those salts right back into the system again.
Next question, John, could you talk a little bit more about the relationship of conductivity and chloride?
Oh, that's a wonderful thing. It's one of those things. It's like um, when you see a graph that somebody has managed to measure both variables, it's just a nice linear relationship. You increase the amount of salt, table salt, sodium chloride, road salt, whatever, into your water, and your conductivity goes up. And to a large degree, it's a linear relationship. Not always. There is one thing to keep in mind. So, if I had time, I'd go grab a graph when we work with deionized water and just add sodium chloride. At the low end, people need to realize that if they're starting with natural water out of a well or out of a nice clean stream and then adding salt, they may have more conductivity due to carbonates than they have due to sodium and chloride. And so their additions won't make that much of a difference. In their mind, they're adding chloride, but they already have a lot of conductivity. So background conductivity in the glaciated areas around here might be around 50. In partially limestone, the conductivity might be in the 200 to 250. And in the real limestone areas, you can have conductivity over 400 as background without sodium chloride being added. Yet, if you started with that low conductivity water and added some sodium chloride, it would go up measurably, significantly. Whereas to the limestone stream, it would barely be a bump. And to deionized water, adding a little bit makes a huge difference because there's no ions in that water. So, but it's a nice linear relationship to a large degree within the limits of what you're starting with.
And John, another question for you too. Could you give a little bit more information about the Maryland criteria of 50 milligrams per liter? And if you have some sort of specific source, they'd love
There
to.
is, I don't know if you have that, Abby. I haven't dug that out in a while, but so they don't have a criteria. It's their way of assigning road salt or salt as a stressor, and therefore a target of remediation. So it's not an EPA approved criteria, but rather, if I remember right, a direct response of them correlating their stream degradation measurements with the concentrations of chloride in their waterways. And where those two lines intersect was, as I remember, 50 milligrams. That was like an internal Maryland report. The Ohio work is a peer-reviewed publication that I can dig around. Remind me, and I'll get that to you, Abby.
Thank you. Yeah, and I might have that somewhere too. I'll have to dig around and I can try to get that to you, Mandy. Another question for you, John. What is the difference between specific conductivity and chloride? Is it just a more generalized search for ions? And what conclusions can we make about chloride with specific conductivity data?
Without breaking down, without some detailed chemistry, or at the very least the chloride strips, understanding what conductivity is measuring for you is a little bit tricky. Knowing what components, because there's so many, especially when we have a national audience here, there's so many sources of soluble salts. And I generalized a lot about just natural. I remember at the beginning I talked about calcium carbonate and magnesium carbonate, but there's sulfates, calcium magnesium sulfates. There are naturally occurring calcium magnesium chlorides. So it's very tricky. And anybody really doing a lot of work with road salt in streams that they want to know well, they should pay to have a cation and anion survey for their water samples, get an idea of what their total ion, positive and negative ions look like in their waterway, and what role, in this case, sodium chloride plays in that picture. And that those can be expensive or cheap. You may have to shop around to get somebody to give you a cation survey for a relatively cheap price. If they do a buy cation and buy anion and at $10 or $20 a pop, it gets expensive.
Thank you. I can take sort of the next two questions. One of the questions which I answered in the chat is, where can we get free water test kits? So for SaltWatch, you can go to www.saltwatch.org, and this information there is in the chat. Or if you are with an organization and you need multiple kits at once, you can email me at saltwatch@iwla.org. The next question there is asking a little bit more about the Winter Salt Awareness Week, which is January 27th through the 31st. You can go to wintersaltweek.org to learn more about that. There's a breakdown of speakers that will be live streamed from the Wisconsin Saltwise YouTube channel. And you can sign up to register for free for those live streams on that website as well. And again, that information is there in the chat. Another question that I can take too, thoughts on liquid spread on roads. So this is sort of an anti-icing that they use. It's a brine application. It's a salt water mixture. So it's about 23% salt and the rest is water. It's much less concentrated than the rock salt that people are applying on the roadways. It's still salt. And so it's considered one of the best practices as far as road salt application currently. It's something that doesn't bounce off of the roadways. It really sticks to the roads once it's sprayed, and it can be applied up to 48 hours in advance of a storm event. So it's easier on a lot of those road salt applicators too. We'll try to do a couple more questions because I know we're way over time right now. Are there other monitoring agencies involved in the other related toxins involved besides salt measurements in the DC metro region? I don't know if we need to be a little more specific with that question or not, because there are a lot of different agencies measuring different things within the waterway.
Yeah, and I could say the Aquapon Watershed Monitoring Lab has existed since prior to the Clean Water Act as well, and has been monitoring for a variety of different things, and recently has started monitoring for PFAS as well. So there's a range, of things that are being explored for sure. And as you say, many agencies that are doing monitoring.
Yeah. Could either speaker discuss the impact, if any, that relative increases in salt concentration at the lower end of salt watch limits might pose for less developed watersheds? So for our limit, we can only, the lowest end that we can measure is about 30 parts per million or milligrams per liter for chloride. So that question again, could either speaker discuss the impact, if any, that relative increases in salt concentration at the lower end of salt watch limits might pose for less developed watershed?
I would just venture to say that if you're at 30, for example, to remember that you're still elevated 3 to 5 times higher, which means that you have, again, depending on the conditions being measured and stuff like that, you're illustrating the connection between our hardscaping and our waterway. And everything that else that's washing off of that hardscaping is coming into that waterway also. So we are just at the very beginning, and it's also an easy one to talk about. But everything we put on our land, whether it's green land or hardscape land, ends up in the waterway. And so if you're measuring elevation, then other things that you're probably not measuring are also elevated. Asphalt sealants, as an example, herbicides and insecticides. EPA just came out with a report that basically said in urban and agricultural areas, pesticides are a clear stressor. This was nationwide, 400 sites. So one of the things that being able to measure salt is to just remind people that their front lawns are part of the stream water, that their parking lots are part of the stream watershed, that what they do ends up in the waterway.
Yeah, and just to follow up on that too, I know we offer road salt applicator trainings to some of our local road salt applicators, and the folks who we contract the training with, they mentioned at our last training that one question that we receive too, but they receive a lot, is what is the most environmentally friendly salt to apply? And I really loved their answer because it was the salt that remains in the bag. So the salt that you don't end up using is the most environmentally friendly salt that you can use. So anything that we do apply is going to have some sort of impact. I think there's 4 more questions, so if you guys have enough time to stay around for these, I really appreciate this. Have you seen effective policies or best practices put in place by city governments to regulate sodium concentration in local water sources? How can cities help reduce road salt pollution?
So in terms of sodium, I can say that there are some states that do have regulation for sodium. Virginia is not one of them. And the levels that are regulated vary, quite a bit. I don't know much about the effectiveness, and I can't specifically, read off the states. I'd have to go back and look at that. But you should know that there are some places that have chosen to do it, even though that it's not, federally mandated to do. So that would be kind of a good place to start to look.
And something I can speak on, especially like the chloride component of that, which is sometimes related to sodium with road salt application. There's some states that are working to do more incentives at the state level. So one good example of that is New Hampshire. They have the Green Snow Pro program, which is a statewide applicator training program where applicators can take that program, pass the certification. If they maintain that certification, maintain the best practices that they learned during the certification training, and take detailed records of the storm events and how much salt they apply and everything, then they are given free limited liability protection against damages such as slips and falls during the wintertime. And the businesses who hire them are also offered that protection too. And so I think incentives like that are something that a lot of states like Minnesota and Wisconsin are trying to strive for, and have put bills at the state level that unfortunately have not yet passed, to try to get something similar in place there to really incentivize those smart salting practices, which then would reduce both the chloride and sodium concentrations from going into the water. So a couple more questions. Are there invasive or non-native plants that have value in terms of phytoremediation of salt?
Yes. We were actually looking at some of the weedy species that, show up whether you want them to or not. Be the way to think about it. Like Rumex crispus, it's like a curly dock, is a really common plant that we find as a weed in most of these detention basins, and it did about as good as cattail. So there is value to weedy species. That one's more of a nuisance than a true invasive because we We were actually encouraged very, very strongly by groups we were working with to not explore the invasives because even if they do have benefits, there's problems with them. So.
And two more questions, I think both for you, Megan. How do laundry detergent sheets compare to pods and liquid?
We don't know about laundry detergent sheets yet. That's actually, since it's a relatively more recent, way of, doing, the washing. It hasn't been explored yet. We mostly focused on things that we could dissolve, and evaluate that way. But that's definitely, an area for future research. I'd have to check. There was one other study that's done on this. It was all through Australia, and I'm not sure whether or not they have done laundry sheets or not. I'd have to look back at that.
And one more question too, is there any plant or plants research or other natural means of removing salt from any runoff that can be beneficial at the same time at the local environment, or better, harvest back the salts that were dispersed and recycle for future use?
I can say that people are using biochar, so like you can stuff like these socks, like you see, for collecting oil and grease, along the side of the road. People stuffing those with biochar, and that can bind salts. And they also sometimes, can take the plants once they've taken up salt instead of disposing them in, say, like a landfill. There's been some exploration of reusing those for feedstock, since livestock require, a certain amount of salts anyway. The concern there, of course, is the other pollutants that these plants may be taking up. But yes, there is active research in how to sort of do more like a green economy life cycle analysis of these kinds of things.
Thank you both so much for being here today. I know we are way over time, so I really, really appreciate all of the time that you've taken today to not only share your knowledge, your expertise, your presentations, to teach us more about this issue and some things that we can do, but also to take the time and answer a lot of these questions that we've had too. So thank you both so much for being here. Thank you everyone in the audience who's attended today who have answered so many or asked so many incredible questions too. We're really, really thankful for all of you to be here and to keep learning together. So thank you so much. Megan and John, thank you very, very much today. So again, this webinar has been recorded and I'll send out an email whenever the recording is up on our YouTube channel, and you can check that out in case you want to go back, learn some more, or if you missed anything. So thank you again so much for being here. Thank you again for our great presenters today. We really appreciate you.